All right, hi everyone. Welcome to CS330. And today we'll be talking about hierarchical RL and skill discovery. These are quite exciting topics. Some of them are a little bit out there, so please ask questions if something is unclear. But first, a few reminders. So the homework 4, the optional one, is due on Monday. And then on Wednesday, we have the project milestone that is due as well. And then one more announcement. Next week, we'll have 2 guest lectures. And these should be really exciting. So we'll have Colin Raffel here, who will talk about big language models. This will be a virtual lecture, so you'll attend on Zoom. And it will start at noon, as opposed to 11:30. So he'll probably talk a little bit about how meta-learning just emerges when you train on big enough data sets, especially with language. So it could be really interesting. And then on Wednesday, we'll have Joshua Sol-Dickstein, who will talk about learning optimizers, which is kind of another way of approaching meta-learning. And he's done a lot of work on the topic. So it would be, I think it will be very interesting to hear what he has to say. And this one will happen in person at the standard time. All right. So let's do a little recall. So we've been talking about reinforcement learning for a little bit, for actually quite some time now. And we have these different kinds of reinforcement learning that we discussed. There's the online reinforcement learning or on-policy reinforcement learning. Then we have off-policy reinforcement learning, where we gather some experiences, we put them in a buffer, and then we have certain set of algorithms that can deal with data like this. And then in the last lecture on Monday, we discussed offline reinforcement learning, where we don't get to interact in the world. We can just access the data that was already collected for us, and then we have to learn the best possible policy given that data set. We also talked about a few different tasks throughout the lectures on reinforcement learning. For instance, we talked about grasping in the single task case when we discussed Qt-opt. We talked about different simple manipulation skills when we talked about empty-opt, such as pushing, grasping specific objects, placing, rearranging, and so on. And then we also talked about goal condition reinforcement learning, where a task is specified by a goal. And this is where we talk about actionable models, where we would present a goal image that we want the robot to achieve, and then the robot will try to get to that goal, as close to that goal image as possible. So far we knew what we wanted, right? We had some kind of task in mind. It was specified in different ways, sometimes as a one-hot vector, sometimes as a language instruction, sometimes as a goal image, but we knew what the task is. We also, if you look at all of these tasks here, they're rather short horizon behaviors, right? So maybe they span tens of time steps, maybe hundreds of time steps, but they're relatively short, simple manipulation skills. And then lastly, we had well-defined tasks and well-defined rewards. So this is kind of equivalent to knowing what we wanted. We knew that we want to optimize for certain tasks, and then we could just go ahead and optimize for them, and then we would test on those tasks. So today we'll talk about something a little bit different, something where we want to maybe discover interesting behaviors. We want to have agents that can discover interesting behaviors on their own, right? So we won't specify the tasks. We'll try to avoid specifying tasks. And instead, we would just want to have an agent that we can just deploy in an environment and have it find out everything that there is to find out about that environment and come up with its own tasks. So one reason to do this is it's also part of how we learn, right? So here is a little time lapse of a baby left unattended, and it does all kinds of different things without being explicitly told to do so, right? And these seem like some targeted exploration behaviors. It's curious about the world, and it explores and tries a whole bunch of different things, and it comes up with its own tasks. We don't have to sit down and specify what is the task that we want the baby to do. In addition to this, there's been some research in biology, some research on frogs, showing that there's actually a small number of core skills that the spinal cord of the frog uses to control all of the movements of the frog. So there's just a handful of skills then the spinal cord can modulate to create a whole variety of behaviors that we experience when we watch frogs, right? So, but there's just a handful of them, and they span this whole variety that we get to observe. There was also a similar research done on human subjects, or that drew a similar conclusion, where they invited human subjects and they asked them to grasp different objects. And then they recorded, using, I think, motion capture system, they recorded all kinds of different grasps, how they were performing the tasks. And then they collected that data set, and then they ran principal component analysis on it, and they found out that most of the behaviors can be understood or can be described by just using a few top principal components. So it seems like it's a similar conclusion where maybe there's just a few core skills that we need to learn, and once we know about those skills and they're well parameterized, then we can use those skills to emerge all the kind of behaviors that we might want in the world. Now, we could try to think of what these skills should be, right? We could try to prescribe them and kind of, through trial and error, find out if these are the right ones or not. But much more natural way would be to have the agents leave them unattended and have them explore the entire world and try all kinds of different things that they might be interested in. And then we can take that and then find the core skills that span that space. All right, there's also a more practical motivation for skill discovery algorithms. So we talked a little bit about this during actionable models, that actually coming up with tasks themselves can be quite tricky. All right, so actually let's run this little exercise. So let's think of a tabletop manipulation scenario. So we have a single arm robot that is in front of a table. It has limited workspace, it's just a single arm. It has a parallel jaw gripper, so it just has two fingers that can just grasp like that. And can you just shout what are the different tasks that you can come up with? What can this robot do? Any ideas? Just shout whatever comes to mind. Yep.
Maybe stack.
Stack, okay. Pick and place, yep.
Push and pull.
Push and pull, okay.
Slide.
Sorry, what is it?
Slide. Slide.
Yep, slide. Mm-hmm. Kind of similar to push and pull, maybe a little different. Mm-hmm.
Rotate things.
Rotate things, okay.
Drop them from elevated position.
Drop them, so you drop them from the table, but then you would need to pick them up from the floor again. Yeah, assuming that you can reach there. Yep, that's a good one. Yep.
Like manipulate some deformable objects like open or close and ropes or pull.
Manipulation of deformable objects, so like pull a rope or put a rope in a certain configuration or something like that. Mm-hmm. Or use a cloth or something like that. Any other ideas? Yep.
Fold something.
Fold something, yeah, also using maybe deformable objects. Cool, awesome, yeah, these are some really good ideas. So altogether, maybe we came up with 20 tasks or so. And what if we want to have robots that can do, kind of anything that you can imagine, right? Like thousands of tasks. What if they're presented with different objects and with some scenarios that we haven't thought of before? And actually coming up with all the different possible tasks, and we want to come up with as many tasks as possible because the more tasks we have, the better generalizations we'll have to new tasks. This is quite tricky. So we run through this exercise when designing this benchmark called Meta World, and we were able to come up with 50 different tasks, and some of them are very similar to the ones that you mentioned. But there's also additional considerations that you should think about when thinking of a benchmark like this. So for instance, tasks need to be at similar level of difficulty so that there's no one task that is way, way harder than some of the other tasks. They should also be accomplishable within a similar time horizon so that you don't have this imbalance during training as well. They also need to be, every single task needs to be solvable using standard single task reinforcement learning algorithm. And sometimes it's quite tricky to get that to work. So there's a lot of different constraints. We were able to come up with 50 of them, but it was actually quite painful to do that. So one reason why we would want to do skill discovery instead is, what if we could just drop a robot in that environment and spawn a bunch of different objects, maybe randomize them from time to time, and have the robot figure out on its own all the kinds of different things that it can do in this environment, and then we can just name them afterwards. All right, so we might need some kind of skill discovery to discover these behaviors. And today we'll also talk about hierarchical reinforcement learning. So why hierarchies and why hierarchical RL? So we are pretty good at performing tests at various levels of abstractions, we as humans. So for instance, I can give you an instruction to bake a cheesecake. And you wouldn't necessarily think about how to contract your muscles to bake a cheesecake. You can think about on much higher level of abstraction. So if you were to plan the first step, you can say, well, first I need to buy the ingredients. And then you can go level lower, and then you can say, well, first step for this is I need to go to the store. First step for this is I need to walk to the door. I need to take a step to do that, and I need to contract a certain muscle to take that step. And we can plan on all these different levels. And if we were to plan some long horizon task like bake a cheesecake on the lowest level of abstraction, it would be an extremely long plan that we wouldn't be able to even think about. So we want to do something similar for our artificial agents. We want them to be able to reason about different levels of abstractions and different time horizons so that they can plan for longer things. And then in addition to this, it seems that these hierarchies and different levels of abstractions are really helpful with exploration. So here's a video of a baby trying to accomplish a task, and it's not really clear what the task is, but it's just trying different things, and then at this point, it's stacked this block, and then it looks for approval whether this was the right task. So in this case, it's doing exploration on this very high level of like, well, I probably need to pick some objects, I probably need to place them somewhere. These are kind of high abstraction skills. It's not really doing exploration on the motor babbling level where it's just like moving its hands in all kinds of different directions and looking for approval. So if we could have something similar, if we could have this much more targeted exploration that explores through higher level concepts, we'll probably have better exploration algorithms. All right, cool. So the plan for today is we'll talk first about information theoretic concepts, and we've talked about a lot of them already. So this might be mostly a review for most of you, but we'll just make sure that everyone is on the same page there. Then we'll talk about skill discovery algorithms. And then we'll talk about how we can use the skills that we just discovered. And then at the very end, we'll also talk about hierarchical reinforcement learning. Cool. So let's start with information theoretic concepts. So we'll start with an entropy. But before we talk about entropy, we have to talk about the distribution. And hopefully at this point, most of you are familiar, or all of you are familiar with what the distribution is. So we can plot it. Here on the x-axis is one-dimensional random variable x. On the y-axis is the probability. And we can look at what kind of values this random variable takes, plot them on this x-axis, and then try to fit a distribution to it, for instance, a Gaussian that shows the probability density of that. So now let's think about what an entropy is. It's an entropy of a distribution, and it's written with this script H symbol. And the formula, if you were to look it up, looks like this. All right? So let's think a little bit about what it actually is. So we have a minus sign, and then we have a log probability, log p of x, under the with the expectation under its own, right? Under its own distribution. So what does that mean? So let's think a little bit. Let's think about how can we make entropy very, very small, right? So how can we take this whole term and make it very small? So for this term to be small, then this term without the minus needs to be big. So what does that mean? That means that we would need to sample, is that right? Yes, we want the full entropy to be small, so then this whole thing needs to be small, so then this thing needs to be big. Actually, let's switch that. Let's make the entropy big. Okay, so let's try to see what would it take to make this term big. So this whole thing needs to be big, so then this part needs to be small. So for this part to be small, we would sample something from our distribution, so we'll sample from our distribution. And then the log probability of that sample needs to be small. All right? So what that means is that I just sampled something, but the probability of me sampling that thing is actually quite low. So I just had, by chance, sampled something that I wasn't actually that likely to sample. So what that means is that basically all of the samples that I'm going to sample are not going to be very likely. In other words, the entropy controls how broad our distribution is. If our distribution was uniform random, right, like if the probability of sampling any potential value was the same, then if I sample that particular value, the log probability of that value will be very small. Right? So the more random the distribution is, the higher the entropy. So in this case, it will tell us how wide this Gaussian right here is, how broad it is. Yep?
Wouldn't the log probability be extremely large for the uniform? Because it would be one, let's say you have like a uniform, it'd just be a constant, like it'd be small, but it should be a 5 unit of QX is very focused, right?
So yeah, so the question was for the uniform distribution, wouldn't the log probability be very large? So if it's a uniform distribution, or let's imagine a Gaussian that is really, really broad, right? Then the log probability for each sample would be relatively small, right? We will spread this peaky Gaussian across the x-axis. So it will be kind of small here, small here, small here, small here. No, log stays the same. Log doesn't change its monotonic function.
But if so, then you have a small probability across all, right? And but if I take the log with small probability, that's going to give me something big, right? And something super negative, which is then going to be positive.
So log doesn't change the value of the so basically the corresponding the big values will stay big. It will just squish them. The smaller values will stay small. Okay. So let's think of another example of a Bernoulli random variable. So let's think of a case where we are just flipping a coin. And we can set the probability, the parameter of the Bernoulli distribution, so the probability with which we'll be getting heads or tails. And that parameter is set here on the x-axis. So if it's 0.5, that means we have an unbiased coin, and it's as likely to get tail as it is to get heads. Now, if we were to plot the entropy of that distribution, dependent on the parameter, it would look something like that. So it basically says that the entropy will be the highest when the coin is very unbiased, right? So when it's kind of the uniform probability where we don't really know what's going to happen, right? The sample is basically, the sample will carry a lot of information in other ways. So the other way you can look at it is that if the parameter is really high, for instance 1 or 0, and if you were to do an experiment, if you were to take a coin that always shows heads, then the entropy of the distribution will be very, very small. What that means is that this experiment is not going to reveal much more new information to you. You already know what's going to happen, right? If you have a coin that always shows you heads, then you don't really have to toss that coin. You know that it's going to be heads. There's not much information in that experiment. But if you have an unbiased coin, then tossing a coin will actually give you a lot of information. So there's a lot of value in performing that experiment, and that corresponds to high entropy. All right, let's talk about another concept, which is KL divergence. So KL divergence, we talked about it a little bit during especially our offline RL lecture, and we talked about it as a distance between two different distributions. So let's define it a little bit more strictly. Let's define it mathematically. So the definition of the KL divergence between two distributions, Q and P, is defined as this. Is defined as the expectation under the first distribution, Q, of the log of the ratio of the two distributions. Right? And you can see that this is not symmetric. The order matters, and we'll talk about it in a second. So we can write it out, because the log of the ratio is the difference of the logs. So we can write it out like this. And then, given that we already know what an entropy is, we can take this term, because this is the log probability under its own expectation, and it's just missing a minus sign, so we can say that this is a negative entropy. So I just switched it here, and this is the negative entropy term, and this term is the same term that we have right here. All right, so this is a distance metric. So let's first see what happens if both of these distributions are exactly the same, right? So we're in Q equals P. So if Q equals P or P equals Q, then we would have this term would just have Q's in here. This term would have just Q's in there, and there will be the two exact same terms. We'll subtract one from the other. The distance will be 0. So KL divergence between two distributions that are exactly the same is 0. So that seems to make sense. That seems like a decent distance metric. But let's think a little bit more about what it actually means. All right, so let's do the following experiment. We will have some distribution that is given to us that is a little bit funky. This is the distribution P of x, and I plotted it right here. Right, so this is what it looks like. And now we'll try to find another distribution, Q, which is a Gaussian, so we are restricted to just Gaussian family, that minimizes the KL divergence between Q and P. Right, so we are trying to find a distribution Q that is a Gaussian that will minimize the KL divergence to this distribution. Right. So first, let's take a look at this term right here. So this says we are trying to minimize the whole thing. So we are trying to maximize this term, right? And this term says that under the expectation of Q, so I'll be sampling from Q, the log probability of P of x should be high, right? So that's how we can minimize that. So that means that we can find some kind of Gaussian so that if we sample from that Gaussian, the log probability of P of x of this funky distribution will be as high as possible. So one Gaussian that fits that description is a very peaky Gaussian right here that covers the same mode as P of x. Right? Does that make sense? So because if we sample anything from that Gaussian, the log P of x, so the probability of this distribution, of these samples here, will be very, very high. All right, so this is the first term. And now we have the second term, which is the entropy term. So we are minimizing the whole thing, so that means we are maximizing the entropy. And to maximize the entropy of that Gaussian, we already know what we need to do. We need to make it broader. Right? So in other words, to find a Q distribution that is a Gaussian, find the parameters of that Gaussian that minimizes the KL divergence between Q and P, which is this funky distribution, we'll end up with a Gaussian that covers the mode of this distribution. Right? So I have one question to you, which is, what would happen if we change the order? Right? What would happen if we were optimizing KL divergence between P and Q and not Q and P? Yep.
Question. So when we're trying to minimize that first term or maximize the expected log probability of P of x under Q of x, why is the result like a peaky Gaussian? Because like wouldn't the entropy or like wouldn't that term always be 0 if we exactly match the distribution? Like
Okay, yeah, that's a great question. So why is this first Gaussian that optimizes only this term, tries to maximize this little term right here, why is it so peaky, and wouldn't we have the best KL divergence if we just match the distribution exactly? Yeah, so these are kind of two separate questions. So let's first answer the second one. So why can't we just find a distribution that's exactly the same? That's because we are restricting ourselves to just a Gaussian family. So the only thing we assume that we can fit is a Gaussian. Right? So this is kind of the best Gaussian we can find that minimizes the KL divergence. Now regarding the second question, why is it so narrow and it's so peaky here, is because if you put any probability mass anywhere else, right, like if we make it a little bit broader, then this term would be a little bit smaller. Right? Then if you sample from that Gaussian, the log probability of that will be a little bit lower. You'll be a little bit lower on that x-axis here. So the best thing you can do is find kind of the most narrow Gaussian that finds the mode of that distribution, and then if you sample from that Gaussian, the log probability, your y value here, would be very high.
So if we were not restricting the Gaussian, somehow we get the power to like model any distribution, then would the minimums be the exact match?
Right, so then the question is, yeah, if somehow we were not restricted to a Gaussian, but we could model any distribution somehow, Would we minimize the KL divergence with the exact same distribution? Yes. So the KL divergence would be 0 if it's the exact same distribution. Yes, there's one question.
Is this related to information gain at all? Like, I know that entropy, when you're subtracting entropies, you have like this concept of information gain, where you are is this like trying to maximize the
Yeah, so all of the terms that we'll be discussing today, so entropy, KL divergence, mutual information, information gain are closely related. And there's close relationships between all of them. We'll talk about some of them in a second. So that will hopefully resolve some of that. Right, cool. So we had this other question, which is what would happen if we change that order? Right, so right now we have this mode-seeking behavior, and that's actually how people refer to it. So we'll try to find a Gaussian distribution that covers the mode of the P of x. So what would happen if we change the order? Yes?
So with the mode seeking, I think because you have P of x at the bottom, like Q of x just has to ensure that it's not 0 when P of x is 0. So in the other case, Q of x is not allowed to be 0 when P of x is not 0. So it's going to like spread over the whole thing.
That's right, yeah. So the Q of x is not allowed to be 0 if P of x is 0. So basically it will try to cover the entire support of P of x. So it will be a Gaussian that goes like this. That's right. And we refer to this KL divergence as a, this one was mode seeking, and this one is mode covering. So it tries to cover all the modes. All right, cool. So one more term. And that's mutual information. We haven't talked much about it, so let's do it now. So mutual information is denoted with the script I, and it's mutual information between two random variables. And it's defined as following, as the KL divergence between the joint distribution of these two variables and the product of their marginals. Right? So let's think a little bit about what this means. So this is how we can plug in our KL divergence formula to this. But first, let's maybe do a little example. So mutual information measures the dependence between two variables, and this is a symmetric measure. So if I told you something about x, and that would reveal a lot of information about y, that means that they're dependent and there's high mutual information between them. And if I could tell you something about x and it doesn't really help you with knowing anything about y, that means that the mutual information is low. So in these two cases, we have a plot of x and y's. So if I did tell you the value of x, if you knew what the x event was, you could you could know actually quite a bit about y, right? You would have, it would reveal quite a bit of information about what y could be. Versus in this case, even though I could tell you what x is, it doesn't really tell you that much about what y would be. These are independent variables. So in the first case, we have high mutual informations. X and y are dependent on each other. And in the second case, we'll have low mutual information. X and y are independent of each other. All right. So we can actually rewrite mutual information as an entropy. So you can do this by doing a little bit of algebra on this formula right here. And it actually results in something like this. So it's an entropy of one variable minus the conditional entropy or the entropy of this conditional distribution of y given x. And you can also flip the order. Right? So let's think a little bit about what it means. So that means that the entropy so the mutual information will be high if this term is high, if the first term is high. So that means that the entropy of the distribution on its own is high, so we don't know what x is going to be. And this term needs to be low. So, but we don't know what x is going to be. It's a kind of almost a uniform distribution, let's say. But if I told you something about y, you would know exactly what x would be. All right? So it's kind of, x on its own is very, very random, but as soon as you know about y, x isn't random at all. You know exactly what x is. And that would mean that there's high mutual information between the two. All right, so let's go through a little exercise. So I'll give you two random events, and I'll ask whether these correspond to there's high mutual information between them or low mutual information between them. All right, so is there high mutual information between x and y, where x says that it's going to rain tomorrow, or it rains tomorrow, and y says streets are wet tomorrow? Is it high mutual information? Yeah, It's high mutual information, right? If you knew that streets are wet tomorrow, you would know that it rains tomorrow. If you knew that it rains tomorrow, then you would know that the streets will be wet tomorrow. But on its own, you can't really tell if it's going to rain tomorrow or if the streets are going to be wet tomorrow. All right, another example. Let's say X says it rains tomorrow, and Y says we find life on Mars tomorrow. High mutual information? No. Yeah, two events are there's a lot of uncertainty in both of them, right? And even though if I told you that it rains tomorrow, that wouldn't really reveal much information about whether we'll find life on Mars tomorrow. All right. So there's one example of mutual information that is actually very useful in robotics. And this is called empowerment, and it was introduced by Polanyi et al. And the form of that mutual information looks like this. It's the mutual information between the next state and the action. So basically the entropy of the next state minus the conditional entropy of the next state given the action. Right? So why do you think it's called empowerment? Any ideas? Yes?
It captures how much the robot can influence the next state it goes to.
Yeah, it measures how much the robot can influence the next state given its own actions. That's right. So it basically tells you how empowered of an individual someone is, right? Like if your actions can really influence the next state that we're all going to see, right? If you're the president of the United States, then your actions are really powerful. They will change what we're going to see next. Right? And the same with robots. So if we want to optimize for empowerment, that means that we want robots to take actions that have high influence on the next state they're going to see. So they'll really influence the environment. All right, cool. So we discussed a few information theoretic concepts, and now we'll use some of them to talk about skill discovery algorithms. All right. So first I'll talk about one algorithm that isn't really a skill discovery algorithm, but kind of gets us in the right mindset. And this is the algorithm called soft Q-learning. So far when we talked about Q-learning, we talked about always taking the argmax of the Q function, right? So we had some kind of Q function that is plotted here, and then our policy would be always trying to take the max of that Q function, and this would be, so it would be a very peaky Gaussian that only cares about the peak of the Q function. But what that means sometimes is throughout training, we'll want our policy to commit always to the current Q function, right? It will always try to find the peak of the Q function and then go with that. Okay? So sometimes it actually can have some catastrophic influence on how the agent develops because it can commit to a solution that is suboptimal. Just initially the Q function isn't well fitted yet, it doesn't represent the environment very well, and it will commit to it fully. So instead what we might want to do is maybe have a policy that doesn't put all of its probability mass on the max of the Q function, but it also puts a little bit of probability mass on another peak that is a little bit lower. Right? This way we don't fully commit to a solution straight away. We'll kind of like, hedge our bets a little bit. All right. There's actually another motivation for this, which comes from neuroscience and inverse optimal control, which talks about the following. If we had a dog and we were asking the dog to come to us, if we only cared about, if we wanted to describe the behavior of the dog, and we were only talking about this argmax of the Q function, then the only trajectory that would make sense within that framework would be the straight trajectory that goes straight to us, the optimal trajectory. That's the only trajectory that we can describe using that framework, right? We always think that the dog is optimizing for the reward. The reward is, you get a little snack when you come to me. So the only behavior that makes sense for the dog within this framework is, run towards me and don't deviate at all. But we know that in reality, maybe there will be something interesting on the way. Maybe the dog will wander around a little bit and the trajectory won't be just straight. And we want to be able to describe all of those trajectories as well. So to do this in inverse stochastic optimal control, people introduced this people basically started talking about a little bit of stochasticity in the policy as well. So it's a stochastic optimal policy. It doesn't mean that the dog always runs directly towards you, but it can also deviate a little bit, and it's still an optimal policy, it's just stochastic. All right. So it turns out that the reward function for a Q function like this includes a term that we just discussed. So instead of just optimizing for the reward as we have done so far, where we are maximizing this whole objective over a number of time steps, we are also going to add an additional entropy term, entropy of our current policy. All right? So what that means is that not only I want you to optimize for the rewards, but I also want you to have a little bit of entropy. I don't want you to commit too early. All right? So I don't want you to be like very peaky. I want this distribution to be a little bit broader. That will result in higher entropy. So it turns out that if you do that and carry out the math, this is our Q-learning algorithm that we had before. It will look very different. It will do very similar, except a few differences. Instead of taking the max over the Q, you'll be taking a softmax here, and the policy won't be just the argmax of the Q function, but it will be actually proportional to the exponent of the advantage. All right, but the more important part is that when you do this, it will result in policies that look like this. So there are a little bit more random policies, right? We are still far from discovering skills, but now we have policies that can do a little bit more. So let's see what that actually results in. So this is a paper by Thomas Harnoya et al. Called Deep Energy-Based Policies. So first thing we can notice is that exploration works a little bit different in these policies. So here on the left, you can see a final policy that is obtained by this ant trying to get to this goal without using soft Q-learning, so with using standard Q-learning. So you can see that the ant just decided the reward is the distance to that goal. So the ant just decided probably early in its training to commit to that path. And then it's really hard to kind of uncommit, to just say, well, maybe I should explore this other path. This is very suboptimal behavior, given that here you're getting more and more and more rewards, but then you realize that it doesn't really get you fully to the goal. However, with soft Q-learning, it's not as committed, so it doesn't just like pick a solution at the very beginning. It actually keeps its options open, and then that allows it to explore a little bit further and then eventually discover the right solution. Right? Let's look at one other aspect of it. So here we are pre-training our ant, and the reward is just the speed. So you can move in any direction, you will just get a reward if you're fast. So here on the left, you will see the resulting policy without this additional entropy term, and on the right, you will see the soft Q-learning policy. So you can see that in this case, all of the ants, so all of the different random seeds basically, are moving towards the same direction versus, let's play this again maybe. Versus in this case, the ant is kind of exploring and going in all kinds of different directions because it doesn't want to commit to a single solution. What that means is that if we were to take this policy on the right that explores the state space a little bit better, it will be probably more fine-tunable, right? Like if we wanted to just then go to a particular corner of the workspace, like right here, then this policy already visited that corner, maybe it already knows how to get there, and we can fine-tune to this. Versus with this policy, it would potentially need to unlearn something and learn how to get there again. And then one other aspect that you get when adding this additional entropy term is the robustness. So here is a robot trying to stack these two Lego blocks. And you can see that this is the soft Q-learning policy, and you can see that you can perturb the robot quite a bit and it still figures out a way to get there. So it explored quite a lot of its state space because it had this additional entropy term that kind of allowed it to explore a little bit more. And now it knows how to recover from all of these different states. Right? If you try just standard Q-learning, it's quite likely that it will just go straight from the initial position straight down, minimize that distance, but then it wouldn't be very robust to any perturbations. All right. So this is, yeah, there's a question. Mm-hmm. Sorry?
Yeah. So in the first ant exploration in the maze, how would this typically be solved in other algorithms like DTG? Would you just like add random action noise that would take a long time?
Yeah, so the question is, how would you solve this ant maze problem in something like DTPG when you don't have additional entropy term? Yeah, so usually to encourage some kind of exploration, you will add some kind of noise, and then you would hope that you would find the right path. but then it will probably be very dependent on the random seed that you use. So sometimes it will do it, sometimes it won't. It will commit to the wrong solution at the beginning, and there's no really good way to recover. But if you look at at an algorithm like soft actor critic, which is kind of another version of DDPG that includes the entropy term, then it should be able to discover the right solution all the time.
So also optimizing for the entropy, does that mean the variance across different runs would be smaller?
Oh yeah, that's a good question. So does that mean that if you optimize additionally for the entropy, does that mean that the variance between different runs will be smaller? Usually it's the case. Yeah. So with DDPG, you're a little bit more reliant on the right random seed, right, that just happened to explore that part of the state space. With SAC, you're always exploring all kinds of all the parts, so you should be able to find a solution better or more reliably. Okay. Cool. All right. So we want to learn diverse skills. So far, we only talked about how we can just learn a skill that's a little bit more stochastic. So when we learn diverse skills, what we want is some kind of way to control the stochasticity. So we want to be able to, for the ant, not just to go in all the directions, but also to say, well, I want you to go up, or I want you to go left, or I want you to go right, and so on. So we'll condition our policy on this additional variable that we'll use to control what kind of skill we want to ask for. So let's call it just a task index or a skill index, Z. And let's say that this is our ant or just some kind of robot, and we want it on its own to explore this environment, so to go in all the different directions, but we want it to be controllable, right? So we want it such that if I set Z to a particular parameter, it will go in one direction. If I set it to some other parameter, it will go in another direction, and so on. So for instance, if I set Z equals 0, it will go up here, and it will result in this green trajectory. If I set Z equal 1, it will result in this trajectory, Z2 in this one, and so on, and they will be all different. In that case, I'm kind of starting to discover the skills, and now they're controllable. It's not just a stochastic policy. So soft Q learning is also referred to as maxed entropy reinforcement learning, or maxed ent reinforcement learning, because we add this additional entropy term that we are maximizing. So why can't we just use maxed entropy reinforcement learning instead? So first, action entropy is not the same as state entropy. So in the previous case, we wanted to make sure that the agent doesn't commit to a single action, right? That kind of keeps its distribution of our actions broad. But that doesn't necessarily mean that it will end up in many different states. It sometimes happens, like we saw in the end, but it doesn't need to happen, right? So agent can take very different actions, but land in very similar states. In addition to this, these maxed ent policies are stochastics, but they're not always controllable. This is what we just discussed, right? So the ant can go in all the different directions, but we can't really say, well, I want you to go in that particular one. So intuitively, what we want is we want low diversity for a fixed Z. So if I told you what skill I want you to know what to do. But high diversity across Z's, right? So if I didn't tell you what to do, then if I were to like marginalize over Z and just look at all of these trajectories, I want them to cover the state space well. Right? That has some resemblance to one of the terms that we were discussing, where one of the term was talking about low diversity if you knew the Z, and the other term was talking about if you don't know Z, or if you don't know this other random variable, there should be high entropy. So keep that in mind. But let's see how we can design some kind of reward function that will get us there. So the intuition is that different skills should visit different state space regions, right? So for different skills, we want to explore different parts of the state space. All right. So we'll try to think of a reward function that is not task dependent, right? So we don't really want to say, I want you to go up or I want you to go to the side. It should be task agnostic. And it should just promote diversity. It should just promote going in all the different directions and be controllable at the same time. So that reward function should probably be dependent on the skill variable Z, right? Because for different skills, it might look a little bit different. So let's just say that it's going to be dependent on that, and then we'll sum over all the Z's to get the reward for the entire policy. And what we would want is, we want to reward the states that are unlikely for any other Z's, right? So for a particular skill, I want you to go to states that none of the other skills would have gone to. Right? That would mean that this skills is as really specific, it's different than all the other skills, and if all the skills were to do that, then we'll get every skill that is very original, and altogether they will span this diversity of behaviors. All right, so here's one idea. Let's train a classifier, this P of Z given S, that tells us, given the state, what skill it came from. Right? We'll just do this using supervised learning. We can roll out a trajectory. We know what Z we set when we rolled it out. We had our policy that was conditioned on Z. And then we'll take this trajectory, every state from this trajectory, and we'll try to fit a classifier that tells us what Z did that state come from. And then in addition to learning that classifier, we'll also set that the reward function for the agent would be to maximize the log probability of Z given S. Right? What does that mean? So both the classifier and the reward function and the agent is trying to maximize this log likelihood. Right? So what does that mean? So the agent itself is rewarded by helping the classifier. Right? So let's think about it this way. We have a policy that produces some actions in the environment, and then we get the states. Policy is conditioned on the skill. And then in addition to this, we have this classifier on the discriminator that takes a state and tells us what skill it came from. And this is the same kind of skill that we input to the policy. All right, so but why does it work? Why does it make sense? So let's go through a little example of how exactly this would work. So let's say we have two different trajectories that were produced by two different Z's. So we are at the very beginning of our training. The agent doesn't really know that different Z's should lead to different trajectories, so both of them are fairly similar. Right, so we produce, this is let's say produced, the green one is produced for Z equals 0, the blue one is produced for Z equal 1. Now we are trying to fit the classifier to it. So let's say that the decision boundary that the classifier learns, it tries to classify these two trajectories. It tries to tell you, given the state, is it Z0 or Z equal 1? And this is the decision boundary it found. So it's not great, but it's doing its best. So now the agent is trying to optimize for the same loss as the classifier. So the agent now is trying to produce new trajectories that will help the current classifier, the current decision boundary. So the next two trajectories that the agent will produce for Z equal 0 and Z equal 1 will be a little bit further apart so that this log likelihood is a little bit better. Right? So it produces two trajectories that are easily distinguishable. And then the classifier optimizes its decision boundary again. So given these two trajectories, it makes a small correction, and now it's a little bit better. And now the agent does it again. So given the new decision boundary, the agent produces two trajectories that help the classifier. And then we adjust the decision boundary and so on. So they kind of play this game, but they're on the same team. Right? The agent is trying to produce trajectories that are easy to classify, and the classifier is then learning how to classify these trajectories. All right, are there any questions to this? Yes?
This is over the whole trajectory, right? Not just the state. Like you do it for every single state. Yeah, so this is a great question.
So this classifier here, what does it take as input? Is it just a single state or a trajectory? So in this particular paper called Diversity is All You Need by Ben Eisenbach and et al., this is just on single state. So it looks at every single state. But you could condition it on something else, on the whole trajectory or something like that. Now, I guess one question to all of you would be, what would happen if we condition it not on just every single state, but let's say only on the last state of the trajectory?
Just wouldn't matter what the trajectory looks like as much. They could look the exact same for most of the trajectory and then diverge it beyond.
That's right. They could look exactly the same way all the way, except at the very end where they would need to diverge, because that's what we will be classifying by. Yeah, that's correct. So you can decide kind of what kind of diversity you want by deciding what you're conditioning this classifier on. If you're conditioning it on every single state, that means every single state has to be different for both of these skills. And there's actually different choices that you can take here. You can condition only on the last state, on the first state and the last state, on all of the states, on all kinds of different things. And there's different works that actually discuss this choice. Yes?
understand this reward function from an information theory perspective. So maximize this reward function corresponds to minimize the negative reward function, which is corresponding to like minimize the entropy of Z given the trajectory of space. So does it mean I want to reduce uncertainty about my skills given the trajectory of space?
Yes, that's a great intuition, and we'll get to it in, I think, 1 slide or 2 slides. Yes, that's exactly correct. All right, so first a few examples of what kind of tasks they could learn, what kind of skills they could learn. So again, they just dropped an agent in an environment, and then they have this very generic reward function that is not environment specific, right? That just rewards diversity and helps this classifier. And then they can try different Z's after this process and just see what they correspond to. So in this half cheetah environment, it turns out that one of the Z's corresponds to the cheetah running forward. The other one corresponds to cheetah doing these back flips or front flips. The other one corresponds to cheetah running backwards. So it can suddenly do all kinds of different things. Here's another example of an ant. So you can see that sometimes ant just does like some random things, jumps in place, does kind of all kinds of different things. Sometimes it runs in one particular direction. And they also tried it in the simpler environment, the mountain car. And you can see that some of the Z's, some of the skills that they learned, actually correspond to solving the task. So sometimes you can kind of by accident stumble upon a skill that solves a task that the original author of the environment had in mind, but it just emerged from this diversity objective. All right, so going back to your question, yes?
So in this case, this corresponds to sort of like unsupervised RL because we're designing like in the mountain car example, it doesn't have the concept of like solving the task.
That's correct. Yeah. So just to repeat the question or the note is that this corresponds to unsupervised reinforcement learning because this is not really specific to a task, right? We designed a reward function that is task agnostic. It doesn't know that the goal of mountain car is to get to the top. Yes, that's exactly right. It's completely unsupervised in this case. All right, cool. So now a connection to mutual information that we talked about just a second ago. So far we talked about the reward function optimizing this log probability. So remember that mutual information is equal to this entropy minus the relative entropy. So let's think of the mutual information between our Z variable, the skill, and the state. Right? So that mutual information is equal to the entropy of Z minus the conditional entropy of Z given S. Right? So now this first part, we don't really have that much control over this. We can just say that every Z is equally likely, right? So we have a uniform prior that will lead to the highest entropy. What that means is basically every skill has a chance to go, right? Like you can sample the Z's uniformly and you don't just focus on one particular Z. So that's easy to do. And then the second part is the entropy of Z given S, and this is exactly minimized by maximizing log of P of Z given S, right? So this tells you that if I know what S it is, then I should, if I told you what S you visited, you should be able to very clearly tell me what Z it came from. So this is exactly the note that you made earlier. And then, so this is the paper called Diversity is All You Need, and then there's a paper actually that came before this paper that discusses a different choice of conditioning. And there's actually a few more called, this one is called Variational Intrinsic Control, and I also encourage you to take a look at that. All right, so we talked a little bit about how we can discover skills. Let's talk about how we can actually use those skills. And how are we on time? Okay. So let's talk about this diversity is all you need paper. So we have this policy now that is conditioned on Z, and for different Z's, it can do a bunch of different things. So let's say we want to now use those skills to accomplish some kind of task that we care about in the world. So let's say we want to have an ant navigate from this point to that point to this point and so on. So how can we use the learned skills to accomplish a task? Any ideas? Yes?
You just sample from your skills condition on what we're talking about is
You can just sample from your skills condition on what your objective is. Okay. Yeah, so you can try different skills and kind of find which ones will work. Yep. Any other ideas? All right. Yep.
Can we just fine-tune on the new task?
Can we just fine-tune on the new task? Yeah, so how would you exactly fine-tune? Okay, great. Yeah, so you could do it the way that you were describing. So you can basically form it as an additional reinforcement learning problem where now you'll learn a policy that operates on Z's rather than on actions. Right? So you'll just learn another policy. Now the action space of that policy is I can command that skill, that skill, and so on. And maybe you act for a certain number of steps, and then after this, you get to choose the next skill. All right, so this is actually what they show in Diversity's all you need paper. And they can get Cheetah to run over these hurdles. They can also do a little ant navigation. And they show some results where it actually works. But one question is, can we do better? And it turns out that we actually can. So what's the problem with this? So the problem with the solution that we discussed just now is that we'll be discovering all kinds of different skills, and some of those skills might not be particularly useful. So sometimes we might just have these skills that correspond to the ant, just kind of like staying in place or jumping a little bit or water bubbling, doing different things, because as long as the skill is different, it will be considered a separate skill. So we maybe want to change the objective a little bit so that we can produce skills that are a little bit more useful. And then the second problem we have is that it's not actually very easy to use the learned skill. So right now the solution that we came up with is that we would learn another policy on top of those skills, which means we need to do another reinforcement learning problem, and reinforcement learning is hard. And now you have to explore in the Z space, which would make it a little bit better, but it's still quite a lot of work that you have to do. All right, so we'll think about one question, which will actually contribute to both of these problems. And the question is, what makes a useful skill? What makes a skill useful? All right, so I'll give you two examples of a skill that is not particularly useful. Right, so we can have this ant that turns upside down, and it's kind of tricky to see what's going on. And then here's another skill where there's this baby playing with Jenga, and it pulls the wrong thing, and it results in a catastrophe. And here's another set of skills that seem a little bit more useful. So here's an ant running forward, and here's this cartoon character juggling. Right? So there could be a lot of opinions what makes skill useful, but there's one approach that was published recently that tries to address this question and says the following. Consequences are hard to predict for skills that are not very useful. And consequences are easy to predict if the skill is useful. So if you're doing something useful, that means it will be relatively easy to predict what's going to happen next. Right? That might be a little bit controversial, but let's run with it and let's see what we get. All right. So this was introduced in this paper called DATS by Archie Sharma et al. And it talks about a different kind of mutual information. So it will try to change the mutual information such that we can incorporate this predictability objective. Right? So we want our skills that are not only novel, but that are also predictable. Right? And we'll think that the assumption is that predictable skills means more useful skills. Right? So this is the mutual information we had before between Z and S. So now we'll have this slightly different mutual information that we'll try to maximize, which is the mutual information between S prime, Z given S. Right? We haven't really talked about this conditional mutual information, so let's talk about it real quick. So this is the definition of the mutual information we had before. So if we make it a conditional, we can just condition everything on this additional conditional variable. So this mutual information would be X, Y given Z, and then this would be a joint distribution condition on Z, and the marginals condition on Z as well. Okay. Right, so we can now rewrite this objective, given that definition, as following. It would be the max of these two conditional entropies. So one entropy says that it should be a high entropy of the next state given the current state, and the other one says it should be low entropy of the next state given the current state and the Z. Right. So what that means is that future, so S prime, what we're going to see next, is hard to predict for different scales if I don't know what Z is, right? So it's difficult to say what's going to happen next. And the second one says the future should be really predictable for a given scale. So if I told you what Z is, then you should be very easily able to tell me what S prime is going to happen next. And if we optimize this objective, that means we'll end up with skills that are predictable, right? So for every Z, this should be very low. So we should be able to tell what's going to happen next. So you can approximate it so that you can actually optimize it, and it results in something like this. And the two important terms are the numerator and the denominator. And the numerator here corresponds to having this additional neural network that we are training, which tells you what S prime you're going to end up in, given the current S and the Z, the skill that you commanded. And we are trying to maximize this whole thing. So that means we are trying to make this log likelihood as high as possible. So we want to be able to tell which state we're going to end up in. And this denominator then says for every other skill, the future should be hard to predict. So if we sum over all the Z's, this should be hard. We're marginalizing over Z here. All right, cool. So what that means is now we have a neural network that we have to fit to maximize this objective, which is this neural network that tells us what next state we're going to see given the current state and the skill. This is fairly similar to something that you already learned about in model-based reinforcement learning, which is the transition model of the environment, right? What's the next state we're going to see given the current state and the action. So we are learning kind of like a dynamics model, but it's a skill dynamics model compared to a conventional global dynamics model that just tells us what's the next state we're going to see given an action. This one tells us what's the next state we're going to see given a skill. All right. And then skills will be optimized so that this skill dynamics will be easier to model, right? So that skills will try to produce such S primes so that this is easy, right? So it's easy to fit that model. Right, and hopefully that should result in a little bit more predictable skills. Right, so let's look at the algorithm. So we would initialize our policy in our the skill dynamics model Q. Then we would sample a skill from a prior. This would be a uniform prior for every episode. In this case, I drew it as a Gaussian, but let's just imagine it's uniform. We sample different skills. And then we would collect new on-policy samples given those Z's, right? So we'll have for this Z, we'll collect this trajectory, for this Z, that trajectory, and so on. Then given that, we can compute the reward for all of those transitions, and we can update our dynamics model. So our reward is now dependent on the skill dynamics model, and we can compute the reward based on this, and we can also update the dynamics model itself. So we do that. And then we can update the policy using any reinforcement learning algorithm. In this particular case, I believe we used SAC. Right, so kind of relatively comparable to diversity is all you need. Now it's just a slightly different model that we are fitting. Before we were fitting this model that tells you, given the state, what skill you're going to end up in. Here we are fitting this model that tells you, given my current state and the skill, what next state I'm going to see. So relatively small change. All right, so this is the algorithm. And we do this over and over again. So let's look at some of the results. So first we see that the things that we learn, if we just look across all the different Z's that we can set, seem a little bit more useful, right? So the and actually, they result to and-anding in all kinds of different directions. And there's fewer of these skills where the and is just like doing random things. We also see that if we were to plot the trajectories that the ant takes in diversity is all you need, in Diane algorithm, they would look like this. Versus in DATS, they're much more, they're much easier to predict, right? They're a little bit simpler. If the ant decides to go in a certain direction, it continues going in this direction because that means that the skill dynamics model is easy to predict, right? It doesn't change its mind all the time, right? So that seems kind of useful. That also means that our humanoid, when we train it on the humanoid, ends up walking in different directions as well. All right, so now we have skills that are maybe a little bit more, they're more predictable, and maybe they're a little bit more useful. But we also had this other problem in the Diana algorithm where we didn't really know how to use those skills, or we had to learn another policy on top of it. So now, because we have the skill dynamics model, we can actually use that model for model-based planning the same way as you did in the model-based reinforcement learning lecture, right? So we can do the following. We can consider different z's, and for every z we can predict what kind of states we are going to see, right? As you did in model-based reinforcement learning. Then the computer estimate the cumulative reward for all of them for a particular task, and then update the planner. So now we can use a planning procedure to tell us which skill to actually use, right? Because for every skill we can kind of unfold it, see what kind of future we're going to see with that skill using our skill dynamics model, and then we can see how that corresponds to the reward that we actually care about. And we don't need to do reinforcement learning here, we can just do planning. Right. So in this case, we'll be planning for skills, not actions. That's the difference to model-based RL, but otherwise, it's exactly the same. And in this case, we also don't need any additional rollouts. We can just think of a task that we want to learn, that we want to adjust our skills to, and do it in zero shot, because we can just imagine what the futures will be for different skills and then put them together. And that actually results in this task where we can have the ant go to these different goal locations, and we can do this without any additional rollouts, right? So we can just optimize offline using the planning algorithm to decide which skills we should be using at any given point, and then we can find the right skills offline and then just execute those skills, and the ant is able to navigate to all these different points. We can also do the same with the humanoid, where we can optimize for which skills to use offline and then use those online to tell the humanoid where to go, which skill to use. So we don't need to do reinforcement learning at this point. We can do it all offline. Right, so a quick summary. We talked about two skill discovery algorithms that both use mutual information, just slightly different mutual informations. And we saw how the choice of mutual information actually influences the algorithm. In particular, in DATS, we use predictability of a skill as a proxy for a skill being useful. And then DATS designed this method that optimizes for both predictability and diversity. And then we showed that we can use model-based planning in the skill space after that. And then, as one of you already mentioned, this opens up new avenues such as unsupervised meta-reinforcement learning or unsupervised multitask reinforcement learning and so on, where we can just, and this is actually described in this paper here by Abhishek Gupta et al., showing how you can just have an unsupervised reward function, like you have in the case of Diane or DATS, and have the agent just explore unsupervisedly and then do meta-learning on those tasks. So now you can do unsupervised reinforcement learning where the agent is coming up with its own tasks. All right, cool. Are there any questions at this point? All right, great. So we have 10 minutes left. Let's talk about hierarchical reinforcement learning. So we know the motivations. We can perform tasks at various levels of abstraction. It might potentially also help with exploration. So it's actually quite tricky to talk about hierarchical reinforcement learning. There's a lot of algorithms out there. So I thought that instead of presenting just one or two of them, I'll just tell you about the design choices that you can make when thinking about hierarchical reinforcement learning algorithms. And then we'll go through some examples and we'll pick what choices the authors made. So I'll be asking you to tell me what choices the authors made here. All right, so if we were to design just a hierarchical reinforcement learning algorithm, it might look like something like this. We have an environment. Environment produces an action, and then we have a policy. This has this superscript L, which means this is a low-level policy. So it takes the state from the environment and then it acts on that environment. And then it takes the next state from that and it acts on that and so on, just like in normal reinforcement learning. But now in addition to this, we'll also have a high-level policy, PyH. And the high-level policy will take the initial state, and then it will command what kind of skill should the low-level policy be doing. Right? And it can command it for a certain number of time steps, or it can command it up until the low-level policy says it's done, but it basically plans or produces actions that are a little bit on a higher level of abstraction. And then let's say that this policy only gets to act for 3 time steps. So then after this, we'll get the next state. And then this high-level policy, given that state, will need to say, well, what should the low-level policy be doing now? All right. So there are 4 different design choices that I want to show you. There are 4 different axes. So first, the one decision that people often make is whether the low-level policy is goal condition or not goal condition. All right. So you can have this low-level policy be conditioned on particular goals. So like a state that you want to get to. So then the high-level policy needs to produce a state here. So a particular state that you need to get to. And then the low-level policy just can do goal condition reinforcement learning. But it doesn't have to command states. It can be some abstract Z, like we had in the case of Diane, for instance, that we don't really know exactly what it means, but it commands it to the policy, and then the policy needs to act accordingly. So that's one decision. The other decision is whether we want to have a pre-trained policy in the low level, or whether we want to train both of these policies end-to-end. Right? So in the case of Diane, in diversity, all you need is we would first pre-train the low-level policy to do all kinds of different things, given a Z, and then we'll, in addition to this, afterwards, train a high-level policy that just commands these Zs. Right? So we had the pre-trained low-level policy, and the high-level policy was trained afterwards. We can also do it all end-to-end. All right. Then the next choice is we can have the low-level policy self-terminate or act for a certain number of time steps. Right? So in this case, it's acting for 3 time steps, and that's it. So this is the budget that it has. But it could be also that the low-level policy has an action that says, well, terminate now. And if it terminates, that's when the high-level policy gets to act again. All right. And then we have the choice that we usually have, which is, are they learning on policy or off policy? So that depends on the RL algorithm you use. All right, so let's run through this exercise. I'll be asking you, I'll be describing a work, some work on hierarchical reinforcement learning briefly, and then I'll ask you what kind of choices the authors made. So let me do the first one to kind of explain how this works. So let's consider the Diane approach. So in this case, the low-level policy is not goal conditioned, right? It's conditioned on the subject variable Z. The low level is pre-trained. It's not trained end-to-end. We didn't discuss this, but actually in Diane, they were running the low-level policy at a fixed rate for a fixed number of time steps. It wasn't self-terminating. And it was all trained on policy as well. All right. So let's go through a few of these examples, and I'll be asking you what design choices did the authors make. So this is a work called Learning Locomotor Controllers by Nicholas Hessedal. And it works as following. So this is a little screenshot from the paper. We have a high-level controller or a high-level policy that is a recurrent controller. And then we have a low-level controller right here. Now this command for the low-level controller is updated every k steps. So it asks it to act for k steps, and then it asks it again. It also uses proprioceptive information. And there's additional task-specific information that is fed only to the high-level controller, but not to the low-level controller. So the high-level controller has some privileged information. Right. In addition, both the high-level controller and the low-level controllers are trained separately. So they first train the low-level thing and then the high-level thing on top of that. They're both trained with policy gradients. And they add hierarchical noise to this controller for exploration purposes. So then they can show something like this, where they have this snake robot, and they can show that by just inputting the noise to the high-level controller, it actually results in some sensible behavior, so we can have some exploration benefits from this hierarchy. All right, and then they show some results showing that that actually works fairly well. All right, so the question to you is it goal condition or not goal condition, the low-level policy? Maybe just say 1, goal condition. Who thinks it's goal condition? Raise your hand. Okay, just a few people. Who thinks that it's not goal condition? Any more people? Okay, yeah, it's not goal condition. We didn't explicitly talk about it. but it just sends a Z command to the low level policy. All right, is it pre-trained or end-to-end trained? Is it pre-trained? Who thinks it's pre-trained? All right, quite a few. Who thinks it's end-to-end? Nobody? Yep, it's pre-trained. That's a little too far. Well, yeah, it's fixed rate. Is it on policy or off policy? Who thinks it's on policy? More or less everybody. Who thinks it's off policy? Nobody? Yeah, it's trained using policy gradient, so it's on policy. All right, cool. Another work. Option critic architecture, work by Bacon et al. So first, an option is described as following. It's actually used fairly often in hierarchical reinforcement learning. It's written by this, it's denoted by this omega, is a triple in which this I omega is the initiation set, so that's when the option can be activated. Then it also has this policy, pi omega, which is a policy, an intra-option policy, so this is the policy, the low-level policy that actually gets to act on that low-level state. And then we have this beta omega, which is a termination function, so this is when the option knows when it can terminate. All right. So here's a little plot from this paper showing a standard MDP where we just act at every time step, and with options, the low-level option gets to act at every time step, but the option itself can jump between them. It's like a high-level policy. And they also, this is a screenshot from the paper where they have an environment that gives you states, and then they have a policy over option here, over options that decides which kind of option, which kind of policy, the low-level option policy gets to go. So it decides whether it's this policy, or that policy. All right, a few more facts. So option is a self-terminating mini policy, so the option itself can decide when to terminate. Everything here was trained together, both the high-level policy over options as well as the options themselves with policy gradients. And here's some visualizations showing that the actual termination conditions that it learned in this four-room grid world actually correspond very often to the exit states, which is kind of interesting. And then they show some additional results. All right, so let's go over the design choices. Who thinks it's goal conditioned? Who thinks it's not goal conditioned? Yeah, pretty much everybody. Great. Who thinks it's pre-trained? Who thinks it's end-to-end? Everyone. Great. It's a little too easy. Who thinks it's self-terminating? Pretty much everyone. Yep, that's correct. Who thinks it's on policy? Yep, pretty much everyone as well. Great. Cool. All right, this one was an easy one. All right, another one, relay policy learning, work by Abhishek Gupta et al. So it works as following. We have a low-level policy and a high-level policy. The high-level policy is sending goals, the actual state goals, to the low-level policy, then gets to act for a certain number of time steps, right? Then it does goal condition learning for the low-level policy as well as goal condition learning for the high-level policy, using hindsight relabeling, actually. All right. So the way this is trained is first we collect demonstrations, kind of in the environment doing all kinds of different things. So for instance, in this kitchen environment, it can be a robot going to all kinds of different locations. And then we do data relabeling where we can take a long trajectory and relabel the high level as well as the low level goals for both the high level policy and the low level policy. Then we start with the imitation learning, and then we continue with policy gradients to do fine tuning using a reward function for both low level and the high level policy. All right, so a few more facts. It's goal condition policies with relabeling. We use demonstrations to pre-train everything. And, it's done on policy with policy gradients. And here are some results. So here is a long horizon goal that we're trying to achieve. And you can see that relay policy learning is able to do this fairly well. So it opens the microwave, moves the kettle, opens the cabinet, and so on. And some other equivalents are not able to do that. All right, so is it goal condition or not? Who thinks it's goal condition? Yep, it's goal condition. Who thinks it's pre-trained? Most of the people. Who thinks it's end-to-end trained? One person. Yeah, so it's actually trained end-to-end. It's pre-trained in terms of both policies are pre-trained with demonstrations, but they're still learned together at all times. Is it self-terminating? Who thinks it's self-terminating? Nobody? Who thinks it's fixed rate? Yep. It's who thinks it's on policy? Yep, pretty much everyone. All right, cool. We have one more algorithm, but I think we're running out of time, so I'll skip this one. And a quick summary. So we have multiple design choices and frameworks for hierarchical reinforcement learning. It usually helps with exploration and with temporally extended tasks, with these long horizon tasks like what you've seen in the kitchen environment. But it can be quite difficult to get it to work. So you're adding an additional policy. You have to optimize for both of the policies. Sometimes the low-level policy is kind of changing under your feet, so you have to accommodate for this if you use an off-policy algorithm and so on. So it's actually quite tricky to get to work. And it also seems like a natural extension for harder RL problems where we have to do longer horizon tasks, but often it's quite tricky to get to work. And there's actually some interesting work talking about why hierarchy sometimes works, and they do a decent analysis showing in what cases it helps and where it doesn't. All right, so we talked about these 4 different things. Thank you very much for your attention, and just to remind you, on Monday, we have the homework 4 due. On Wednesday, project milestone is due. And next week, please attend the 2 guest lectures that are going to be really interesting, I think. Thank you.